All right, y'all. So this is the HL version of the energetics test coming right off the SL part that we finished in the last video. So this is the HL additional material. So starting with number one, what is the correct combination of delta H and delta S values for a reaction that is only spontaneous at high temperature? For spontaneity, we're looking at delta G, Gibbs free energy, and that must be less than zero to be spontaneous. So we're looking for a delta G value that is less than zero. We know that our equation for delta G is equal to delta H minus T delta S. So in this case, we can go through each example and see how it would affect it. I'm going to start from the bottom example. If we have a negative value here and we subtract from a temperature value times a negative value, we might get a positive, we'll get a positive value because a negative times a negative is a positive. So part D, this would not only be spontaneous at high temperatures. In fact, the higher the temperature, the more positive our negative T delta S will be, and the more likely that we're going to be a positive delta G. So it can't be D. Similarly, B has that same problem. When delta S is equal to a negative value, the higher our temperature, the higher our temperature value right here is, the less spontaneous this reaction will become. So it can't be B either. Furthermore, if we look at C, C has a negative delta H, negative delta H. I'll just write this a little better. Negative delta H minus T positive delta S. So what we'll get is we'll get some negative value here, some negative T delta S, and we'll have some negative value here. And this means that no matter what temperature this is, we will always have a negative delta G. So C is always spontaneous. Therefore, it must be A. Has to be. If we look at this analytically, we can see that a positive delta H minus T delta S, which is also positive, this will be negative, this will be positive. Delta H is honestly usually measured in kilojoules, while delta S is in joules, meaning that most of the time this will create a positive delta G. However, if this temperature is high enough, the negative can therefore outweigh the positive and we get a negative delta G. Therefore, this is spontaneous at a high temperature, A. Number two, at which temperature could delta H, delta S, and delta G all be positive? So let's go ahead and look at our equation again. This is still delta G equals delta H minus T delta S. So we just noted that at high temperatures, we can have a positive delta S, positive delta H, sorry, reverses, and still have a negative delta G. So we know from our first question, it can't be that. All right, let's look at low temperatures. At low temperatures, T is essentially negligible. When you see low temperature, you can basically assume T is approaching zero. And you can start using sort of limits and that sort of thinking, which means delta S doesn't matter. Delta S could be positive, delta S could be negative, who cares? But really, it means delta G is reliant on delta H. And if delta H is positive, then delta G is positive. So at low temperatures, we can achieve delta G, delta H, and delta S all being positive. All right. Which value has the largest, which compound has the largest value of lattice enthalpy? Well, lattice enthalpy depends on two things. One, it depends, well, you know what? Let's simplify it further. It depends on one thing, that one thing being electrostatic interactions, meaning it depends on the magnitude of charge and the distance between charges. Why does lattice enthalpy depend on that? Well, lattice enthalpy, if you think about it, it's the enthalpy needed to break those bonds, or the energy needed to break those bonds in a in an ionically bonded lattice. And so if we want to break those bonds, we have to see how strong they are. And the stronger those bonds, the larger the value. So we're looking for magnitude of charge. When I look through this, I notice that these all go with something that has a 2 minus, 2 minus, 2 minus, and 2 minus charge, while our cations are 1 plus, 1 plus, and so on and so forth. So magnitude is actually not important in this one because they all have the same magnitude of charge. Now we have to look at distance between charges, which is really just another way of saying size or atomic radius. And the smaller, the stronger. The smaller equals stronger. And we know that because you can think about when you put magnets together, the closer the magnets are, the bigger the force. This is a really strong force, while two magnets far away is just a very little weak force. So we have to see which of these have the best combination of smallest atoms. So we're comparing between sodium and potassium, and sodium is smaller than potassium. Then when we compare between oxygen and sulfur, oxygen is smaller than sulfur. So we're going to use the smaller ones, and it's going to be A, NaO. And that's how we can solve this one really quite easily. What are the signs of delta H and delta S for a reaction that is non-spontaneous at low temperatures, but spontaneous at high temperatures? Hey, guess what, y'all? This is exactly the same as the one we did for number one, delta H minus T delta S. We want something that's spontaneous at high temperatures. So we know the answer is going to be D, but let's just go through that one more time. A nice way to think about it, and a different way to think about it before, is if we look at low temperature, let's just assume T equals 0. And at high temperature, we can assume T equals infinity. So at low, when T equals 0, delta G equals delta H. And this becomes 0. So in this case, if delta H is positive and delta G, therefore delta G is also positive. So that's non-spontaneous at low temperature. All right, the second example, as T goes to infinity, delta G equals negative delta H, or sorry, equals, whoops, delta H minus infinity delta S. In this case, if delta S is positive, then this becomes a negative infinity. If delta S is negative, this becomes positive infinity. At which point, you don't really care about H. So we're trying to find a time when this is spontaneous, so negative delta G at a high temperature. All right, so delta S must be positive. The answer is D. All right. Number 5, consider the Born-Haber cycle for the formation of sodium oxide. What is the lattice enthalpy in kilojoules per mole of sodium oxide? So what we're looking for in this case is this. So to do that, we're going to use Hess's law. So we're going to start right here. And the first thing we're going to do is go up. And because we're going opposite the arrow, this negative is going to become a positive. So right away, it cannot be C or D because we're starting with 414. All right. From there, we're going to add 2 times 108. Cool, they both do that. We're going to add 249. Cool, they do that. We're going to add 2 times 496. They do that. Then we're still following this arrow. We're going to subtract 141. All right, our answer is A. To finish this out, we are then going to add 790. And we continue with our answer being A. So that's kind of how you follow the Born-Haber cycle. Just go with the arrows, and if you're going against the arrow, flip the sign. All right, moving on to number 6. Which represents electron affinity? Well, you have to remember that electron affinity is the gain of an electron. Gain of electron. So we have to find the one that literally adds an electron. This removes it. This removes it, which, for the record, uh, these two are ionization energies. This does nothing with electrons, so our answer must, by default, be B. All right. Which change would result in the largest negative value of delta S? So which is basically removing entropy the most. So basically, when you're trying to figure out which is removing entropy the most, you want to see the most gas going to the most solid, or something within that range. It could be gas to liquid to solid. But anything moving to a more solid form of matter is going to be a decrease in entropy. So I notice I have liquid going to gas, probably not that. I notice I have solid going to solid plus gas, probably not that. I have liquid going to solid. Yeah, that's a decrease, liquid to solid. And I have gas to solid. Ooh, gas to solid is even greater of a decrease. And something more is this is 1 mole to 1 mole. Well, this is 2 mole gas to 1 mole solid. So it's got to be D. That's a really big decrease in entropy right there. All right. Which reaction has the greatest increase in entropy? This is the exact opposite of the last one. So now we're looking for solid to gas or solid to liquid to gas. So we have 2 gas to 1 solid. No. We have 1 solid to 1 solid and 5 gas. That's a really big increase. We have 1 solid to 1 solid and 1 gas. That's a big increase, but not as much as B, so we'll disregard it. And we have 1 gas to 1 solid. Nope. Our answer must therefore be B. All right, moving on to number 9. Which equation represents the standard enthalpy of atomization of bromine, Br2? So we're going to take Br2 and turn it into Br. You'll notice that for this reaction, we're not adding or taking any charges away because it's just separating the atoms. This is breaking that bond. This is also a standard enthalpy, meaning we have 1 mole. We're only looking for 1 mole of our product here. So we're going to end up with A. It's the only one that goes to 1 mole. You'll notice D does too, but you have to be careful because D goes from a liquid to a liquid. And you may say, Mr. Garcia, well, why is that the same? Why is that not the same? Well, when you have, first off, when you have just one atom of something flying around in space, that's always going to be a gas because the definition of an atom of a gas is something that does not have any shape or volume, and the particles are alone. They're not bonded to any of their neighbors through intermolecular forces. So it can't be that. Which change has the greatest increase in entropy? Okay, we have solid to gas, we have gas to liquid, we have gas to solid, and we have liquid to solid. So these three right here are all a decrease. So it's got to be A. One little trick here is that you could also ask greatest increase and go from solid to liquid or liquid to gas. And which one is a greater increase in entropy? Well, this is still greater because the particles are physically separating and going everywhere. It also takes a whole bunch more energy to do that. Number 11, which of the following reactions is there an increase in entropy? All right, so we're going from 1 solid to aqueous to 1 aqueous and 1 liquid. Okay, so we are removing our solid and going to a liquid. So that is an increase in entropy. Here we're going from 3 gas to 1 gas. That's a decrease now. Here we're going from 3 gas total to 2 solid. No, that's a decrease. Here we're going from 3 aqueous to 1 solid and 2 aqueous. That is also a decrease. We're going to the solids. Gotta be A. All right, moving on to 12. Define standard enthalpy of formation. So you need a couple things. You need to mention STP, standard temperature and pressure. So that's going to be 273 Kelvin and 100 kilopascals. And you also have to mention that we make 1 mole of product. All right. Number 2, use the enthalpy cycle below and data in the table to calculate the value of delta HF for ethanol. So we have to find this value right here, delta HF for ethanol. So that means we are starting down here and we're trying to get up to here. So the question is, how do we in fact do that? So we look at our chart and we notice that instead we can do kind of a roundabout method. If we take this one and add them together, we get that one. Then we go from that product and we go against the delta H of combustion, so a negative delta H, we can instead get our enthalpy of formation. So we're going to go ahead and write out what we just put down. Delta H F of ethanol, C2H5OH, is equal to this one, 2 delta HF standard of CO2 plus 3 delta HF standard of H2O. And then this one going against that minus delta H of combustion of ethanol. So we can go ahead and use the values in our chart right here. 2 times negative 394 plus 3 times negative 286 minus negative 1,367. We add all that up and we get negative 279 kilojoules per mole. All right, and that's how we solve that one. Define the term average bond enthalpy. This is just straight up a definition. This is the enthalpy or heat needed to break specifically 1 mole of bonds in gaseous state and then averaged over similar compounds. So you specifically need these 2 sections. That's 1 mark, and averaged over similar compounds is your 2nd mark. All right. Ethine reacts with hydrogen in an addition reaction shown below. Use the data in section 12 of the data booklet to calculate the change of enthalpy for this reaction. So first off, you kind of want to try and draw these so you know what bonds you're looking at. So here's ethine, and then finally we go ahead and we get ethane. Oh, whoops, ethane. And I'm not going to draw hydrogen. No, I guess I will draw hydrogen. There's hydrogen. So we can see the bonds that we're making. And we have 2 of these. All right. And there's our chemical reaction drawn out. So when we're doing bond enthalpy, we have to remember that for this, our formula is delta H is equal to the sum of the delta H of the bonds breaking minus the sum of the delta H of the bonds forming. So let's take stock of what we have. I notice that we have in this reaction up here 2 hydrogen bonded to carbon bonds plus 1 carbon triple bond to other carbon. I add that to 2 times hydrogen single bonded to hydrogen. Over on the other side, I'm just going to drop this down a little bit. On our products, we are subtracting carbon bonded to carbon plus 6 carbon bonded to hydrogen. All right. I plug these values in with data from my data booklet, and I get a total of negative 291 kilojoules per mole. And there we go. And with that, we have finished the HL test. Hopefully this helps. Have a good one.